oscillations today. 2 of those definitions come from mechanics, 2 of those definitions come from waves. And now we're going to do a classic Unit 5, we're going to go right back to Unit 3 and look at the mechanics. But we're also going to bring in Unit 4 and look at oscillations, the crossover between mechanics and waves. Let's see how they fit together. This is the best example I could find to hand of an oscillator, and it shows you a really useful application as well. Pendulums and clocks are really simple examples of oscillations. You can see here it's got a time period of a second. Frequency must therefore be 1 Hertz. How would you describe one complete oscillation of this pendulum? A complete oscillation is where you go back to the same point moving in the same direction. So it's easy between the amplitude, it's the time it takes to go from 1 and back. You might want to measure a complete oscillation from the centre as well, in which case it would be the time it takes for it to go to one extreme, to the other, and then go back, moving in the same direction. A really common error that people make with oscillations is they say that one complete oscillation is the time it takes to get from here to here. Hopefully you can see why that is incorrect. I just thought I'd start with that because it's a really common error people make, is that they fail to correctly define one complete oscillation. And obviously, if you get that wrong, that can lead to a whole cascade of errors. A complete oscillation is where you go back to the same point moving in the same direction. The technical term for an oscillation is a simple harmonic motion. It's just the words that we use. I know in the book it goes straight to the definition of simple harmonic motion, but I want to take a step back and explain where that comes from. I'm going to try and use this pendulum to explain as best as I can. If I take the pendulum, whenever the pendulum is in this centre position here, it's in its equilibrium position. Remember what it means to be in equilibrium as well. The resultant force has to be what? 0. And therefore, we know that the weight of the pendulum, and let's call it a tension in that piece of wood, are balanced. The resultant force on it at the equilibrium position is 0. If I move the pendulum to one of its extremes, if I move it to the amplitude, I can literally feel in my finger the resultant force. It wants to just go back to the middle. If you drew the force diagram as well, you would see that the weight acts directly downwards and that this wooden beam provides a tension at some angle. The vertical component of that tension would balance the weight, but it does have a horizontal component acting towards the middle. The more I push my pendulum away from its equilibrium position, the greater the size of the resultant force. As I let the pendulum return to the equilibrium position, the resultant force goes back down to 0. And so on, as it returns to its furthest amplitude, the resultant force increases again, and so on and so on. And it's this which causes our oscillation. The resultant force acting on that object, not only directed back towards equilibrium position, but it's also directly proportional to the displacement from the equilibrium position. That leads us to the definition of simple harmonic motion. Simple harmonic motion is any motion where the acceleration of the object is directly proportional to the distance from the equilibrium position and directed back towards the equilibrium position. As it says in the book, Acceleration is proportional to displacement from the origin and always directed back towards the equilibrium position. Acceleration is maximum at the amplitude, 0 in the middle. Hopefully it's not too much of a stretch to notice the velocity of this oscillator as well. As the oscillator passes through the equilibrium position, it's moving at its fastest. I know it's not impressively fast here, this is just a clock, but it is moving with its highest velocity in whichever direction. At the extremes of its motion, at the amplitude, that velocity is instantaneously 0. Remember that velocity and acceleration are not the same thing. In this case, we see a 0 velocity where we have maximum acceleration. Recall the definition of acceleration is the rate of change of velocity. At the extreme of motion, the rate of change of velocity, therefore the acceleration, is the highest, because the velocity is going from forward to backwards through 0. So to summarise, the velocity is a maximum in the middle at its equilibrium position, where the displacement is 0, and the velocity is a minimum at the amplitude, at the maximum displacement, because that's where it instantaneously has to go through 0 in order for it to change direction. If you ever forget it, just picture a pendulum and think about where's it going fastest, where's it stopped. It has to stop at the amplitudes because it's changed direction. So at this stage we know how and why the force works. That gives us the definition of simple harmonic motion as a motion where the acceleration of the object is proportional to its displacement from the origin and always acting back towards the origin. We can write that definition as a proportionality relationship. If I say that A is proportional to minus x, it has to be a minus. That tells me that the acceleration is proportional to the displacement x, and the minus says always back towards the equilibrium position. When my displacement is positive in that direction, the acceleration will be negative in the negative direction. And vice versa, when my displacement is negative, my acceleration will be in the positive direction. So that minus there is crucial. And if you're ever asked to use this equation, make sure you say A is proportional to minus x. It's the defining equation for simple harmonic motion. In this definition of SHM, the constant of proportionality is a thing called angular frequency. It has symbol omega. You might remember in the last book something had symbol omega as well, and that's because they have the same definition, 2 pi over t. Angular frequency is 2 pi over t, the same way that in a circle omega was 2 pi over t as well. For an oscillation, they have a frequency. Don't forget that frequency is 1 over time period, so you might see it written as 2 pi f as well. Omega, 2 pi over t, can also be 2 pi f, 2 pi times the frequency. Don't worry about angular frequency. As that standard answer says, all you need to be able to say is that angular frequency is 2 pi times the frequency. Frequency is the number of oscillations per second, angular frequency, 2 pi times that. That is all. Angular frequency is there in order to make the cosine function work. There's no deep physics to it. It's important to recognise that all oscillations vary sinusoidally, like a sine wave. If I start my oscillator at its maximum displacement and plot a graph of displacement against time, it will be a cosine graph. The amplitude of that graph, how high it goes up the x-axis, it would be the amplitude of my oscillator. It would vary between a maximum and minimum. So if I plot x as a function of time, what I see is the displacement varies as a cosine. That cosine is multiplied by the amplitude. So A goes out front, cos And then inside the brackets of the cos is the angular frequency times time. The reason why the angular frequency is there isn't important. Just know that if it wasn't there, this wouldn't work. It's there in order to make this cosine function give you the correct value at time t. Just need to know that x equals a cos omega t. What do they make you do with that equation? They make you look at it and realise where the values are. So they might say, what's the amplitude? And you have to look at it and you say the amplitude is 0.85. They might ask you what the frequency is, and so you'd look at it and you'd think, omega is 2 pi f, so 6 divided by 2 pi is the frequency. It's not too hard. They could ask you to sketch it, of course, and again, what do you do whenever you sketch a graph? You just put a few values in and you plot it. You know the extreme, the height of it is going to be the amplitude, and you know that the time period can easily be found from omega. Omega is 2 pi over t, so just swap it. 2 pi over omega is your time period. So they could ask you to sketch it too. Don't be intimidated by this equation. You use them all the time in maths. So you use cosine all the time. This is not hard. You'll only ever be plugging numbers into it. That's all. Remember, in this case, whenever you're using the cosine function, it has to be in radians mode. Cosine has to be in radians mode in oscillations, because 2 pi f, that angular frequency uses 2 pi. That's the complete oscillation in radians. So your calculator just must be in radians mode. It'll give you the wrong value if not. If displacement varies as a cosine, bear in mind it might be a sine, just keep your eye out for that. It depends where it starts from. Does it start from the middle or does it start from the edge? Usually it has to start from the edge in order for it to actually oscillate at all. So usually displacement is a cosine. It might be sine, you'll deal with it, same thing. If displacement is varying as a cosine function, velocity, the rate of change of that, must vary as a sine, and the acceleration must vary again as a negative cosine. You don't need to do the maths on velocity and acceleration, but you could be asked to sketch it. An important feature of oscillations, which is drawn on this page, is that they are what we call isochronous. Sounds really posh, doesn't it? Isochronous, was he a Greek god? Isochronous, iso means the same, chronos, time. All of these properties, the acceleration, the velocity, the displacement, all of these properties vary with the same time period. And so this page in the book is showing you how the displacement, the velocity and the acceleration all vary with respect to each other. Velocity is the rate of change, isn't it? So technically that's maths, isn't it? You differentiate this to that, but you don't need to do that in physics. You would do it in maths. You'll notice that each one is 90 degrees out of phase when the displacement is maximum, the velocity is 0. The acceleration is the minus version of displacement because of the definition of SHM. And all of these curves are isochronous. They have the same time period. Now, if you're really good at calculus, you can derive these next equations, but you don't need to. You just need to know what they are. The highest value that velocity can take is omega a. You don't need to even care where it comes from, you just need to know that Vmax is omega a. By the same reasoning, we can learn that the maximum acceleration is minus omega squared a. So these two relationships, you just need to know them. The maximum velocity is omega a, the maximum acceleration is minus omega squared a. That follows from the definition of SHM as well, doesn't it? The maximum acceleration should occur at the amplitude, and it should be back towards the centre. Just one final thing remains. What if I want to find the velocity at a given point in my oscillation? Well, there's an equation for it. The velocity at a given point on an oscillation, it could be positive or negative. The velocity might be that way when the pendulum's going that way, but it might also be in the opposite direction when the pendulum's going back. And so this is the only equation in physics to feature a plus or minus sign. You need to think, will the pendulum be that way or that way? If you don't know, then keep it as a plus or minus, because that's important. The velocity as a function of displacement is equal to plus or minus omega multiplied by the square root of amplitude squared minus displacement squared. You will know x because you'll be given it in the question. X is your variable that you're going to change. You will know omega because you've got the frequency, 2 pi times frequency is omega, and you'll know the amplitude. So really, all you need to worry about is putting the right displacement in and getting the right velocity out. They don't even like to rearrange this equation. You know, if you put this in an exam, people would have an absolute flap trying to rearrange it. So they don't even ask you to do that. They just ask you what's the velocity, and you put in an x, and hey presto, there it is. So I know there's a lot of ideas to take on board there. Started from the very basics. Where's the force a maximum? How's that related to displacement? We looked at omega and how that's pretty much the same as it was in the previous book. Omega is the angular frequency, 2 pi divided by the time period of an oscillation. 2 pi times the frequency, because frequency and time period are inversely proportional. We saw how we can use a cosine function to describe the motion and the displacement as a function of time. It goes from a maximum through 0 to a minimum and back again, and so it traces out that beautiful cosine function. If displacement is varying as a cosine function, velocity, the rate of change of that, must vary as a sine, and the acceleration must vary again as a negative cosine. All of those oscillations are isochronous. They have the same time period regardless of what their values are. How do I do the calculations? Well, if I want to know the velocity, it could be positive or negative, so that's plus or minus omega multiplied by the square root of amplitude squared minus displacement squared. If I want to know what the maximum velocity is, then that is just omega multiplied by the amplitude. If I want to know what the maximum acceleration is, that is minus omega squared multiplied by the amplitude as well. I perfectly expect you to be watching that summary thinking, so much information going on there. And yeah, because it normally takes me 2 lessons to do all of that. I just can't really do that now. Because normally I would say, here's an introduction, do some exercises. Normally I would say, you try this thing in the book. And normally you would slowly but surely piece together oscillations. I don't expect you to watch this video once and understand it all. And that's a weird thing to say, because in a lot of the other videos so far, that has been my aim. But I want you to now go back, rewatch sections of this video in line with parts of the book, pause it, slow it down, reread the notes in the book. And most importantly, whenever you're doing an oscillations question, there is literally a mini equation book of things that you could use. I recommend you always open your equation book just to remind you which ones are available for an oscillations question. Make sure you understand what you're doing, slow down, practice. People have already been speaking to me about the photoelectric effect, saying, I ran through it and I feel really bad now because I didn't get it. Well, save yourself that feeling about oscillations, slow right down, commit time to learning this material. You'll massively benefit from it. Rewatch this video again, but slowly. Later on in this week, I'll be back to talk about kinetic energy in oscillations and how that's conserved. It's another way of looking at them. They're lovely and they're a really, really common bit of physics. Even if you go on to do chemistry as a degree, you will be looking at simple harmonic oscillators because it's how the electrons move in a bond. No matter what you go on to do, you will come across oscillations again. So commit the time now to learning the basics. You owe it to your future self. Have a go at some of the questions, have a go at this little summary, and most importantly, rewatch that again, but slowly and part by part. I'll see you later in the week.